Namaste and a very good evening to all of you. I welcome you to my channel, The Outlier. My name is Mithu. In today's video, I'll be talking about a very important variable selection method, which is called as the forward selection method. Even before I proceed to demonstrate how to use the forward selection method in SPSS, may I request you to subscribe to my channel, also like and share my videos. Let's begin by asking a simple question. What exactly do we mean by the forward selection method? A forward selection method is a variable selection method in which the variables are sequentially entered into the model. I repeat, forward selection method is a stepwise variable selection method in which the variables are sequentially entered into the model. The first variable considered for entry into the equation is the one with the largest positive or negative correlation with the dependent variable. Now, what is the criteria for entry into the model? Any variable is entered into the equation only if it satisfies the criteria for entry. If the first variable is entered, the independent variable not in the equation that has the largest partial correlation is considered next. This procedure is repeated and only stops when there are no variables that meet the entry criteria. To demonstrate how the forward selection method works in IBM SPSS, let me use a data set which is called as car sales dataset. This is part of the samples folder which is provided by SPSS. You're seeing the interface of IBM SPSS now. As you can see here, this is the file menu. I will be going to an option which is called as recently used data. Here, the very first option is what is called as car sales 1. You can see here, this is the data set that I'll be working on in today's video. As the name itself suggests, car sales, we are talking about vehicle characteristics in this data. The first variable is the manufacturer's name. Then we have the model of the car. Then we have very important variables like sales value. I want to use sales as the dependent variable. Further, I also have other important variables like resale value, type, price, engine size. As I scroll to the right side, you see other very important variables like horsepower, wheelbase, width, length, curb weight. Then you have fuel capacity and mileage per gallon. So in this data, I've got 11 independent variables and one dependent variable. There are two ways of doing this. First is to run a simple enter method. To perform the linear regression model, you can go to the analyze menu. Here you have an option which is called as regression. The second item from the top is what is called as linear regression. You can choose the second option in the list of features. You can see here, this opens up a dialog box which is called as linear regression dialog box. Here it is asking you to specify the dependent variable and you can specify the list of independent variables under the independent section. Let me choose sales and push it in the box for dependent variable. So sales is the dependent variable. The vehicle characteristics like resale value, vehicle type, price, engine size, horsepower, wheelbase, width, length, curb weight, fuel capacity, and fuel efficiency will be my independent variables. Now, I've chosen 11 independent variables. Are all these variables important? Do all these variables drive sales? We do not know. So under the method option, you can see there's a feature which is called as enter method. This will give you a linear regression model output with all the 11 variables. To run a linear regression model output, you need to specify the dependent variable as well as the set of independent variables and hit the OK button. This is the first table in the output. You can see here, this is the output window of SPSS. The first variable simply specifies the variables that it has entered. The second table, we have what is called as the model summary table. Here, let me draw your attention to a very, very important statistic, which is called as the R-square statistic. R-square is also called as coefficient of determination. I repeat, R-square is called as coefficient of determination. R-square lies between 0 and 1. If the value of R-square is close to 1, it means that the model fits the data well. On the other hand, if the value of R-square is close to 0, it means that the model does not fit the data well. Here, the R-square value that I have obtained is 0.34, or in other words, 34.6%. Roughly, I can say 35%. So what does this mean? This simply means that 35% of the variation in the dependent variable is explained by the set of independent variables that we have used. Further, you can look at the ANOVA table. ANOVA stands for analysis of variance. The purpose of this video is not to explain each and every item, so I'll just look at some of the important statistics. You can look at the significance level, which is 0.000. Since this significance level or p-value is less than 0.05, we can go ahead and conclude that R-square is significant. So 35.6% of the variation that we have obtained is a significant value. Let me scroll down, and this is very, very important. Please look at the model coefficients table. You have the list of independent variables. Then you have what is called as unstandardized coefficients. Under this, you see two important columns, that is the beta coefficients as well as the standard error. For some of these variables, we have a positive value, and for others, we have a negative value. Next, we have what is called as standardized coefficient. I repeat, these are standardized coefficients. In fact, these standardized coefficients are called as the beta coefficients, whereas the unstandardized coefficients are simply denoted by B. If your goal is to compare which variable is better, it's always better to use standardized coefficients. On the other hand, if your goal is to build a predictive model, unstandardized coefficients would be preferable. In this table, I would draw your attention to the significance level. If the p-value for any variable is less than 0.05, you can say that such a variable is important and that particular variable is significantly contributing to the dependent variable. When you look at the first variable, that is 4-year resale value, you're getting a significance level of 0.911. Please observe this. This is 0.911. Clearly, the significance level is greater than 0.05, implying that resale value is insignificant. Statistically speaking, resale value is insignificant when it comes to predicting sales. Very important observation. When you look at the second number, this corresponds to vehicle type. Here, the significance value is 0.04, which is less than 0.05. And since this value is less than 0.05, you can go ahead and conclude that vehicle type is statistically significant. Further, when you look at price in 1,000, the significance level is 0.734. Clearly, it is greater than 0.05, implying that price is statistically insignificant. If a variable has a significance level of 0.05 and above 0.05, I can say that it is insignificant. On the other hand, if the p-value or the significance level is smaller than 0.05, then you can go ahead and say that this independent variable is statistically significant. So we are already seeing that there are a lot of variables which are statistically insignificant. You can say that resale value is insignificant. Further, price as a variable is insignificant. Then you have horsepower, which is statistically insignificant. Further, you have width, which is insignificant. Length as a variable is insignificant. Fuel capacity and fuel efficiency are also insignificant. So out of the 11 variables that we have used, enter method has built the model with all 11 variables. And it's very, very important to observe and note that out of these 11 variables, there are at least 5 variables which are statistically insignificant. So given that there are a lot of variables which are statistically insignificant, the one question that we need to ask ourselves is, why do we need to build a model with insignificant predictors? I repeat, why do we need to build a model with insignificant predictors? Is there a way in which we can select only useful variables and drop useless variables? I repeat, is there a way in which we can select only useful variables, statistically significant variables, and drop off those variables which are statistically insignificant? So to answer this question, we would have to use what is called as a variable selection method. Let me show you in second stage as to how we will be using the variable selection method to arrive at the best subset of predictors. What you have in this particular model is not the best subset of predictors. What you have is a list of 11 variables, and enter method has used all these 11 variables to assess the statistical significance. Now, let me go back to the data set. This is the data set that I've been working on. Now, I'll be performing a variable selection method. Let me use analyze, come to regression. The second option from the top is what is called as linear method. I repeat, the second option from the top is what is called as linear method. How do we select a particular variable? To select a particular variable, what you can do is specify the method of selection. The default method is enter, and we have just now performed regression using the enter method. Let me click on the drop-down method. My apologies, the drop-down menu. When I click on the drop-down menu, you see there are 4 important options apart from enter. The first is what is called as stepwise, which is a variable selection method. Then you have what is called as the remove method. And the last 2 methods are what is called as the backward elimination method. And the final method that you have is the forward selection method. In the forward method, the emphasis is on selecting the variables. And in the backward method, the emphasis is on elimination of a particular variable. I repeat, in the forward selection method, we emphasize on selecting the most important variables. In the backward elimination method, we emphasize on eliminating useless or unimportant variables. Forward selection method works on the criteria of correlation coefficient. To be more precise, it works on the partial correlation. So I'll be using the forward selection method to arrive at the best subset of predictors. You can see here, I've got 11 variables. I'd like to identify the best subset. Let me go ahead and click on the OK button here. Wow. You can see here, this is the output window. In the output window, what you're seeing is the very first table tells you which are the most important variables which drive sales. The first model has been built using only wheelbase as a criteria. The first model has been built using wheelbase as the independent variable. The second model has been built using curb weight, and the third model has been built using vehicle type. Now look at the method for entry. It says forward, within bracket it says criteria is that the probability of f to enter must be less than 0.05. I repeat, the probability for a variable to enter is that it should be less than 0.05. So if the criteria is met, a variable will be chosen in, or else it will not be selected. So the entry criteria is observe the probability of f. The probability of f must be simply less than 0.05. So in this way, we can arrive at the best subset of predictors, the first being wheelbase, second being curve weight, and the third being vehicle type. So these are the three best subset of predictors out of the 11 that we had. Now, let's look at the model summary table. The first model is built using wheelbase. When you're trying to explain the variation in sales using only wheelbase, the R-square value is 16.6. You're using one single predictor and you're getting an R-square value of 16.6. Please observe, when you include curve weight along with wheelbase, in the second step, R-square jumps to 24.5%. And the final model, which is built using all the three variables, namely wheelbase, curve weight, and vehicle type, you get an R-square of 0.298. Roughly 30% of the variation in the dependent variable is explained by the three variables, namely wheelbase, curve weight, and vehicle type. Let's look at the ANOVA table. When you look at the ANOVA table for the first model, please observe the significance level. It is 0.000, which is clearly less than 0.05. For the second model, again, the significance level is less than 0.05. And for the third model, the significance level is again less than 0.05, indicating that the final model that we have built using wheelbase, curve weight, and vehicle type is a statistically significant model. Let me scroll further down. Now you can see I'll ignore the first two models and focus on the final model, that is model 3. We are getting the coefficients for only three variables, namely wheelbase, curve weight, and vehicle type. Now, how do we interpret this value of 5.8? It simply means that if you were to increase the wheelbase of a vehicle by 1 unit, sales would increase by 5.8 units. Look at curve weight. The unstandardized coefficient value is minus 60, which simply means that if you were to increase curve weight by 1 unit, sales would drop by 60 units. Are they statistically significant? Let me look at the last table. Please observe the p-value here, 0.000 for wheelbase. For curve weight, you have 0.000. Again, for vehicle type, you have 0.00, implying that each of these variables is statistically significant. Let me compare the coefficients table that we have obtained, which is very concise, very easy to understand. We can build the model with only three variables, namely wheelbase, curve weight, and vehicle type. Compare this with the results of enter method. When we use the enter method, we had a whole list of variables. We had to build the model with all 11 variables. And the biggest problem here that we observed was that the significance level was exceeding 0.05. Now we have a better model, and hence we are able to better control the output results. One other advantage here is that when you use variable selection method, not only the final list will be lesser, it will be manageable. There's one additional advantage, and that is, to a large extent, when you look at the final list of variables, they do not suffer from the problem of multicollinearity. I repeat, they do not suffer from the problem of multicollinearity. To a large extent, any of the variable selection methods can be used to remove and solve the problem of multicollinearity. Let me scroll down here. You can look at the excluded variables list. There's a big list here. And in this final model, SPSS gives you a list of variables which it has excluded. And please look at the p-value. The p-value for each of these is bigger than 0.05. Since these variables are statistically insignificant, that's the reason as to why SPSS has removed these variables. The final model can be built using just the 3 variables, namely wheelbase, curve weight, and vehicle type. With this, I've come to the end of today's video. In today's video, we have seen what exactly is forward selection method. We have compared the enter method with that of forward selection method. We also compared the value of R-square. The R-square value did not drop significantly. It was very close to 35%, implying that we are not making a huge compromise as far as the overall value of R-square is concerned. I request you to subscribe to my channel, also like and share my videos. Thank you very much for watching this particular video. Have a great day ahead.